Assalamu alaikum. Hello everyone. My name is Abdullah MANFI. Today, uh, I will discuss how virtual memory behaves on modern many-core system with NOMA and why this combination can become a uh, performance bottleneck. My focus will be on the main challenges and the key optimization techniques that operating system can use. Virtual memory optimization in high-density multi-core system. This is the outline. Firstly, we will talk about problem landscape, normal behavior, hotspot contingent, and location policies, dynamic migration. Problem landscape. Uh, As in this slide, as core counts increase, traditional virtual memory becomes a scalability pain point. Memory is no longer unified, accessing data on a remote NOMA node can be several times slower than local memory, so some cores may stall waiting for data. At the same time, shared structure like TLB and page tables become hotspot. Page table walks add extra latency and also create extra traffic that uh, competes with normal data loads and stalls. If we If we look at the cost stack, a TLB hit is very cheap, but a TLB mixed with a full-page table work plus a remote memory access can easily dominate the critical path of execution. Secondly, we will talk about NOMA behavior. NOMA systems are built from nodes. Each node has a set of cores and local memory. Local accesses are very fast, while remote accesses go through interconnects and are much slower. A common policy, first touch a page is placed on the node of the CPU. The first accesses. This means that the placement of the threads and data slightly side the latency profile of the whole application. As the fraction of remote accesses increase, the instruction the cycle of the application drops significantly, especially for memory-bound workload. Hotspot contingent. Confidence in the mini-core. We have page faults, storms, TLB shutdown, logs contingent, build row latency. Contingent is other major issues when many cores fall on base at the same time. We can get page fault storm that uh, serialized execution and increase kernel time. A TLB shutdown where one core send IBI to others to TLB uh, the other TLB also become very expensive on many core systems. Shared lock protecting page tables or a lecture structure can turn into bottleneck. Uh, there is also hidden calls page table walks generate memory traffic that blocks shared cache, useful application data, and DRAM bandwidth. Location policies. To address these issues, operating system and allocators use NOMA-aware policies. First touch combined with peer nodes helps allows memory to be allocated from specific NOMA nodes. When we bind thread to the same nodes that holds their data, we improve locality and reduce remote access traffic. Another important techniques is the use the huge base standard like for KB base need many TLB and larger page table. A huge base such as 2 megabyte or 1 gigabyte cover more memory with fewer entries, reduce, reducing TLB misses and sharing a base table. This can improve both bandwidth and CPU efficiency from large working set. Dynamic migration. Static placement is not always enough, so some systems apply dynamic optimization kernel or use space symbol and symbol access patterns, identify hot space and decide whether migration page to the another node to work to cost. As at the same time, schedules can be empty where they try to co-locate threads with their data and use their nodes to run uh, quads and this reducing both remote memory traffic and cross-node cache and helps keep most access local. Real-world impact. These ideas have direct impact on real system. Consider a database server running on the 4 nodes NOMA machine with native placement. If most data sits on one node while threads run across all nodes, throughput many drops to around half of the peak because of the remote latency. With NOMA aware placement, where data can threads are uh, collocated on each node, the system can reach close to peak throughput. In cloud environments with many FM or the uh, and poor guest page placement can create noisy neighbors, for example, and quality of the server exposing NOMA technology to guests and Constructing placement using groups helps maintain performance issues. Future and takeaways. There are still important limitations and filing as overhead and access patterns can change using migration and uh, the main takeaway is that virtual memory has become a primary performance lever on many core NOMA systems, and virtual memory and NOMA optimization is very analog scalable performance. Thank you for listening, and I will show you my report, IEEE report. This is my report. Thank you for listening, and see you in the next time.